Hello students, welcome to the Power Electronics Lab. In this section, we are going to learn on single-phase semi-controlled converter with R and L load, symmetrical and asymmetrical. Circuit diagram of symmetrical and asymmetrical with RL load. So in the first circuit, as a symmetrical, the second one is a asymmetrical circuit. In the symmetrical, we are using two thyristors and two diodes with R and L load. In asymmetrical also, two thyristors on left hand, two diodes on right hand side with R and L load. The arrangement of thyristors and diode you can observe in the symmetrical and asymmetrical. MATLAB simulation implementation on symmetrical RL load. Input voltage 50 peak equal 35.35 RMS and frequency 50 Hz. R is equal 12.5 ohm, L is equal to 6 millihenries. This is a block diagram of simulation as a symmetrical circuit. MATLAB simulation implementation on asymmetrical RL load. In this circuit also, input voltage 50 peak equals 35.35 RMS and frequency 50 Hz. R equals 12.5 ohms, L is 6 millihenries. Now in this you have to observe the thyristor current and diode current in the simulation circuits. Pulse generator parameters. In the parameter, once you selected the pulse generator parameter, pulse type time base, time, use simulation time, amplitude 1, period 0.01, pulse width 5%, phase delay 0 multiply 0.01 divided by 180. Here 0 is nothing but your firing angle. Instead of 0, if you are placing 30, that is your firing angle 30. Like that you have to vary the firing angle 0, 45, 90, 120. MATLAB 19A simulation block and path. So we want to design simulation circuit in the MATLAB. So these are the blocks required. With the help of this path, you have to design the MATLAB circuits in the simulation. Now we'll do the simulation using MATLAB. Double click on the MATLAB icon desktop. MATLAB will be opened. In this, double click on Simlink or go to New, select here also Simlink model. In the Simlink, double click on blank model. So your model is opened with Untitled. This model you have to save with some file name. For this, go to File, Save as exp6. Save. Now your model is saved with exp. Here you are designing your simulation circuit. First we will do as a symmetrical circuit. For this you need a block. For this, go to library browser. In this, our power electronics path is first select as a Simscape. Under Simscape, electrical. Under electrical, specialized power system. Under this, fundamental blocks. So fundamental blocks. First select power GI, add to your model. Next, electrical source. We are doing as a single phase, means select as a AC voltage source, add to model. Elements, series RLC, select series RLC branch, add to model. Measurements, voltage measurement, add to model. Current measurement, add to model. Power electronics, in this you required as a one is thyristor, one is a diode. select first diode, add to model and thyristor. Next you require as a mean and RMS block. For this control and measurement, in this select measurement, select mean, add to your model. Select RMS, add to model. You need a bus selector. For this, under Simscape, commonly used block, select bus selector. You need a scope and display. For these are available in the under Simscape sinks. Select scope, add to model. Select display, add to model. Now almost we collected all the blocks. Now we'll separate all the blocks. Now first we'll arrange the thyristors and diodes. Rotate the thyristor by pressing Ctrl plus R. Now naming is I am giving naming thyristor 1. T1. So you required one more thyristor. T2. Diode, Ctrl plus R, rotate. Name it as a D2. D2. D1. Now first connect thyristor T1 anode to D2 cathode, T2 anode to D1 cathode, T1 T2 cathodes join, D2 D1 anodes join. Now double click AC voltage source. Peak amplitude now we will give as a equivalent RMS voltage, that is 35.35, and frequency 50. Apply and OK. Now from AC voltage 1 terminal to current measurement plus terminal, current measurement negative terminal to T1 D2 anode cathode joining point. Another terminal of AC voltage source to T2 and D1 joining point. Now rotate the series RLC branch by pressing Ctrl plus R. So in that we will select as a R and L. Double click series RLC branch, branch type select RL. R is 12.5 ohms, L inductance is 6 millihenries. Apply and OK. Now then required one more ammeter also here. This is output current measurement, where the T1 T2 cathode joining point, connect current measurement positive terminal, negative terminal to R and L load terminal, one terminal, R and L other terminal connected to D1 D2 anode points, joining points. Now you require one more bus selector. Select and copy. One is to connect T1 E terminal to bus selector 1, D2 E terminal to second bus selector. Now double click the bus selector, remove unknown signal, select thyristor voltage, thyristor current, apply and OK. In the second bus selector also double click, remove unknown signal, diode voltage, select diode current. We require one more scope, select scope on. So here you are getting 4 waveforms. So you have to give as a to increase the input terminal to scope. Double click the scope, go to configuration, properties, number of input port to 4, apply and OK. First 2 for thyristors, remaining 2 are diode. Now we can add 2 more means and RMS. Can add display also 4 numbers. This scope also change the input terminals to 4 number. Go to configuration properties, number of input to 4 points, layout 4. Now again what happen here, you want to turn on the thyristors. For this you require as a one pulse generator. This will be available in the common user book under Simulink sources. Select as a pulse generator, add to model. Now and to change the configuration of pulse parameter, double click this one, parameter, pulse type time base, use simulation time, amplitude 1, period 0.01 and pulse with 5%, phase delay 0, multiply, braces start 0.01 divided by 180. Here the 0 is your firing angle 0. In place of 0 you are placing 30, that is firing angle 30. Like that you have to vary the firing angle 0, 45, 90, 120. Apply and OK for different runs. Now connect same pulse generator to T1 and T2. Now we'll connect as a input voltage measurement. Now you need an across the load means select one more voltage measurement. Connect across the R and L. Now first connect the scope to input voltage, input current, output voltage, output current. Now these mean connect to current measurement, RMS to current measurement, mean of this one is connected to voltage output terminal, RMS to voltage measurement output terminal. And double click on mean block, fundamental frequency should be 50. RMS block also 50. Fundamental frequency 50. RMS block so 50. For example, if you no need of RMS block, you can remove. Current mean and voltage mean. From this also, mean current of thyristor, mean current of diode current. From this, these means, two means are measuring. One is a thyristor current, second one is a diode current. Now you can change your simulation time to 0.5 seconds and save your file now by pressing save button. Now here, now running the simulation, now in this we placed as a 0 multiply into 0.01 divided by 180, nothing but your firing angle is 0. At firing angle 0, now we are getting as a results. Run your simulation by pressing run button. Now you can observe the input and output voltages in the scope. You can label it input voltage, input current, input current, output voltage, apply and OK. Output current, apply, OK. Now when alpha is firing angle is 0, you got these are the output waveform. Now take a screenshot of this one, save in the folder. Now we'll change the firing angle to 30 degrees, 45 degrees, apply and OK. Run your simulation by pressing run button. Now double click the scope. Okay, otherwise change your simulation time to 0.5 to 0.1. Then you will get as a clear waveform. In the previous firing angle 0 also you can change it to 0.5 to 0.1. Double click scope. Now this is one complete cycle. In that, during this is a positive of cycle, when it is 45 degrees, start to conducting output voltage. Now this all firing angle is 45 degrees. Take a screenshot, save in the folder. Now change it to firing angle 90 degrees. Again run your simulation by pressing run button. What happens, you observe when you changing the firing angle, the average voltage and average currents also changing across the thyristor current and diode currents also can observe. Again open the scope. Now when it's output voltage when exactly 90 degrees, This is a waveform at firing angle 90 degrees. Now firing angle 120. Apply and OK. Run your simulation again by pressing run button. Open the scope. Now you can see when it is in 120 degrees, start to conducting. When firing angle 120 degrees, these are the output waveforms. Take a screenshot and save in the folder. This simulation on symmetrical circuit. Now we'll do as a asymmetrical circuit. Just we'll modify the circuit. Instead of thyristor, place the diodes here. Connect this from bus selector to diode 1. Now we can constructed as a asymmetrical circuit. Now 2 thyristors on left hand side, 2 diodes on right hand side. Now change your firing angle to first place as a 0. Apply and OK. Now we are measuring the thyristor current and thyristor voltage in bus selector 1, diode voltage, diode current in the, this is D2, this is T2. Okay, save your file again because we changed this thyristors and diodes by pressing save button. Now we changed firing angle to 0. Run your simulation by pressing run button. Again, now you can observe the waveforms in the scope. At when firing angle is 0 degrees. This one you can take a screenshot and place in the folder. Now change it to firing angle to 30 degrees. Run your simulation by pressing run button. Again, double click the scope. Now you can observe when, so give as a all for 45 degrees, 30. Run your simulation by pressing run button. Why? Because in the symmetrical we have done firing angle 0, 45, 90, 120. In asymmetrical also we'll run the firing angle 0, 45, 90, 120. For each firing angle you have to take a screenshot of all the waveforms, place in the folder. You can observe in the scope also. Now it is 45 degrees, start to conducting. Like that you have to change this 45, 90, 120 degrees and run your simulation and take a screenshot of this circuit diagram of asymmetrical. In the previous circuit also, symmetrical also, take a screenshot. All you have to save in the folder. Now we'll do the hardware implementation. Symmetrical semi-controlled converter. For this you require as a power module. The power module will give 3-phase supply, single phase supply and DC supply. In that you have to choose only single phase supply. Now second one is SCR diode power module. In this SCRs and diode contains So we have to choose T1, T2, D1, D2 components. Next is required as a firing circuit. How we are using in the simulation pulse generator, like that the firing circuit is required for generating pulses to turn on the thyristor. And resistive load R is equal to 12.5 ohms. How we are connecting from black and blue between these two terminals, resistance is 50. So 50, 4 resistors connected in parallelly. So 50 by 4 you will get as a 12.5, and L value is, that is inductance value between black and red, 6 millihenries. Now we have to observe the waveform in the scope. So it is required as a digital storage oscilloscope. This is a hardware part. Hardware implementation on asymmetrical semi-controlled converter. For this also power module required, SCR diode power module, firing circuit, T1, T2 thyristors, D1, D2 diodes, resistive load, resistance value is 12.5 ohm, inductance L is equal to 6 millihenries. Now we want to see the waveforms required as a digital storage oscilloscope. Now we will do the hardware on symmetrical circuit with R and RL load. For this, equipment required: power module, SCR diode power module, firing circuit, resistive load, inductive load, and digital storage oscilloscope. In power module, the power module will give 3-phase supply, single phase supply, and DC supply. In that we have to choose as a, for single phase circuit, so select as a single phase AC voltage source, and symmetrical circuit as a thyristor 1 and thyristor 2, diode 1 and diode 2. These are the thyristors and diode required from the SCR diode power module kit, and the resistance value is 12.5 ohm. How will make the 12.5 ohm resistance? So now from black and blue as a 50 ohms, select 4 50 ohms resistor connected in parallel, then we'll get as a 25 ohms. 0 to 0, 0, 0, 50 of one resistor, second resistor, third resistor, and fourth resistor. Now we'll get between black and blue, the resistance value is 12.5 ohm, and inductance value between black and red as a 6 millihenries. Now we'll make the circuit from the power module AC voltage source to input of the SCR diode power module MCB. Now T1 and T2 thyristors cathodes join. Now choose the diodes D1 and D2 anodes join. T1 anode to D2 cathode, T2 cathode to D1 cathode. Output of the MCB of single phase supply connected phase to T1 anode, D2 cathode joining point. From MCB neutral point output terminal to T2 the anode and D1 cathode joining point. Load other terminal, one terminal to T1, T2 cathode joining points. Load second terminal to inductor, one terminal. Inductor other terminal to D1 and D2 anodes joining points. Now this has a symmetrical circuit. Now to turn on the T1 and T2 thyristors will give as a gate pulses. Now switch on the 3-phase main supply. Now to turn on the thyristors of T1 and T2 will give as a gate pulses from the single phase firing circuit. Now we connected as a T1 and T2. Pulses we are applying from the firing circuit. Now we'll switch on your 3-phase main supply. Switch on power module MCB. Switch on single phase AC voltage source. Switch on SCR diode power module MCB. And switch on firing circuit driver switch on. Now slowly increase the voltage to circuit by pressing the plus button reaches to 35.35. Now adjust the voltage to 35.33 or 4. So these are the digital value, it will be varying. So adjust the 35.3. Okay, now adjust the voltage division to 20 divisions. Now we got an output across R and L load. For this, from the waveform you want to measure the mean and RMS voltage by pressing measurement button. This waveform at firing angle is 0. This waveform you have to capture in the PC. Open choice desktop. Select instrument. Select USB. OK. Now here the TDS 2002 be DSO connected and get screen by pressing this button. Now you got an output across R and L and when firing angle is 0. This waveform you have to save in the folder. Now we'll adjust the firing angle to 45 degrees. That time is 2.5 milliseconds. Now adjust the delta T as a 2.5 millisecond, then firing angle is 45 degrees. Okay, you can observe the cursor 1 0 volts reference and cursor 2 also millisecond is nothing but 0 volts. Now this output voltage at R and L load and firing angle is 45 degrees. Now at 45 degrees firing angle, measure the mean and RMS voltage by pressing measurement button. Now we can observe the RMS and mean voltages and frequency also. This waveform also capture in the PC by pressing get screen button. Now firing angle at this between these two cursors, the delta T is 2.5 milliseconds, nothing but firing angle is 45 degrees. This waveform also save in the folder. Now we'll do the firing angle to 90 degrees. Adjust the firing knob to 90 degrees. Nothing but the delta T should be, you will get as a cursor, press cursor button and adjust the cursor to where the firing angle is applied. Now you will get delta T, observe as a 5 milliseconds is nothing but your alpha is 90 degrees. When alpha 90 degrees, now you can observe the mean and RMS voltage by pressing measurement button. Now RMS and mean frequency you can observe. Now when alpha is 90 degrees, This waveform you have to capture in the PC. In the open choice desktop, select get screen button and press the get screen button. It will be captured the waveform in the DSO. Now between the cursors, the delta t is 5 milliseconds. Then you will get as a at 90 degrees RMS voltage and mean voltages. Now we'll do firing angle to 120 degrees. The delta t as a 6.6 milliseconds. Now press cursor button, adjust the cursor. Now you can observe the delta t as a 6.6 milliseconds is nothing but your firing angle is 120 degrees. This waveform also you have to capture and measure this RMS and voltage mean voltages by pressing measurement button. At firing angle 120 degrees, this waveform also you have to capture in the PC. In the open choice desktop, get screen button. By pressing get screen button, the waveform will be saved in the PC. Now between these two cursors, the delta t is 6.6 milliseconds. Nothing but firing angle is 120 degrees. Now we are done as a symmetrical circuit with R and L for 0, 45, 90, 120 degrees we are done. Now we will do as a asymmetrical circuit. For this, first make it off your SCR diode power module off, and before that bring back to your firing angle to 0 and make it off your SCR diode power module MCB off and switch off your AC single phase voltage source. Now we will reconstruct as a asymmetrical off control converter with R and RL load. Now make the connection from single phase AC voltage source to SCR diode power module MCB input side and T1 and T2, T1 anode to T2 cathode join, T1 cathode and D2 anode cathode, T1 cathode to D2 cathode and D2 anode to D1 cathode, T2 anode and D1 anode. Now from the MCB of output terminal to where the anode and cathode joining of R phase, from the MCB output neutral to D1, D2 anode cathode joining point. From the resistive load to T1 cathode and D2 cathode joining point. Both the cathodes are joined. There we are making as a resistive positive terminal. From the resistor other terminal to inductor, inductor other terminal to T2 thyristor and D1 anode joining point. Now replace the gate triggering pulses to T1 and T2. Now we are giving gate pulses to T1 and T2. Now in asymmetrical circuit we are using as a thyristor 1 and thyristor 2. According to will make the gate firing circuit pulses to your the thyristors also, T1 to T1, T2 to T2. Now switch on your 3-phase power supply. Switch on your 3-phase power module. Switch on AC voltage source from the power module. and switch on SCR diode power module MCB on and firing circuit driver switch on. Now slowly increase the voltage to 35.3 by pressing plus button. Now we are adjusted to voltage to circuit 35.3 and this current as a input side current, and you got an output voltage across R and L when firing angle is 0. Then these waveform from this you will measure as a mean and RMS voltages, press measurement button, and these waveform you have to capture in the PC. Open, select instrument, select USB, OK, and here instrument is detected and press this button, it will be capture the waveform, get screen button. Now we got an RMS and mean when firing angle is 0. Now we'll vary the firing angle to 45 degrees, that equivalent 45 degrees equivalent time is 2.5 milliseconds. Now adjust the cursor, press cursor and measure the delta t time using two cursors. Now you can observe the delta t is 2.6 will consider as a equivalent to 2.5 milliseconds. Now alpha is 45 degrees. When alpha is 45 degrees, you got this output voltage. From this, you will measure mean and RMS voltage by pressing measurement button. Now RMS and mean voltage appears. This waveform you have to capture in the PC and press the get screen button. Now between these cursors, the delta t is 2.5 milliseconds, is nothing but firing angle is 45 degrees. Now we will apply the firing angle to 90 degrees, that equivalent delta t is 5 milliseconds, and press the cursor button and adjust the cursor. Now you can observe delta t is 5 millisecond exactly and your firing angle is 90 degrees. When alpha is 90 degrees or firing angle is 90 degrees, and you can observe the mean and RMS voltage by pressing measurement button. Now this waveform also you have to capture in the PC by pressing get screen button. Now this output voltage waveform at firing angle is 90 degrees. Now adjust the firing angle to 120 degrees, that delta t time is 6.6 milliseconds, and press the cursor, adjust these cursors. Now both are cursor 1 0 volts and cursor 2 also millisecond is nothing but 0 volts. Now you can observe delta t is 6.4, little bit adjust the cursor to. Now you can observe the delta t is 6.6 is nothing but your firing angle is 120 degrees. At 120 degrees, what are the mean and RMS values we are getting? You can observe by pressing measurement button. That waveform you have to capture in the PC. So by pressing get screen button. Now between these cursors, the delta t is 6.6 milliseconds, and these waveform you have to save in the folder. So we are done for different firing angle 0, 45, 90 and 120. All these waveforms we are saved in the folder. In that particular 45 degrees of the waveform you have to attach in the result file. Now we are done single phase, symmetrical and asymmetrical with R and RL load firing angle of 0, 45, 90 and 120. Now again your firing angle bring back to 0. Make it your circuit off, means MCB of your SCR diode power module, and reduce the voltage to AC voltage to 0. Switch off AC voltage source button and switch off power module MCB button and switch off your 3-phase main supply. Results. Symmetrical. First one is symmetrical. Attach the circuit diagram of single phase semi-converter with RL load in MATLAB Simulink. So when we are doing simulation, you design the circuit, right? That wave circuit here you have to attach. Attach the waveform of input voltage, input current, output voltage, output current, Simulink. We are done for different firing angle, but at 45 degrees you have to attach the waveform here. Third one, attach the waveform thyristor voltage, thyristor current, diode voltage, diode current at firing angle 45 degrees. Attach the waveform of output voltage at firing angle 45 from the experimentally. Here you have to attach. Next is asymmetrical. Attach the circuit diagram of single phase asymmetrical semi-converter with RL load, MATLAB Simulink. That is also here you have to attach the circuit diagram. Like that, remaining also at firing angle 45 degrees of all this you have to attach. From the experimentally also attach the waveforms. Observation of symmetrical semi-controlled converter. One is the from the Simulink results. Now second one is the experimentally results for firing angle 0, 45, 90, 120 degrees. Both Simulink and experimentally. Observations: asymmetrically semi-controlled converter with RL load, Simulink and experimentally firing angle from 0, 45, 90, 120 degrees, Simulink from Simulink and experimentally also place the resultant values. Thank you.